All right, I think we'll kick off, and I want to say thank you for showing up, and welcome to this presentation when I'm going to walk through a little bit about machine learning and share a little bit of insights. And in front of you here is the agenda I thought we'll walk through. So one of my reasons for running this presentation is when I started to study this field a couple of years ago, it's a field with a lot of jargon, words, and it's pretty technical. And I thought I'd put together a presentation on how you can actually start to use it and how you can apply it and what it means, for example, for architecture. Because that's information I found was pretty hard to get to. So this is the agenda, and we'll walk it through with you during this presentation. So let's start off, and warm welcome to everyone for taking this journey with me. Okay, so why machine learning? Well, maybe you heard about a couple of situations where machine learning, or which is a specific technology inside artificial intelligence, makes a difference. Maybe you just this is something that you have stumbled upon in articles, or maybe it's because it's the new hot field right now. But if we look at a little bit of different situations where artificial intelligence already today makes a difference, I'll highlight a few use cases. So one is autonomous cars, where machine learning is being used and utilized in order to detect what's happening around the car. Another example, also a vehicle example, here is from BMW using machine learning to detect oversteering. It's also being used in detecting fake art, so actually being able to see which art is true and which is fake. It's being applied in a numerous amount of recommendation engines. Facebook being one example, Spotify another. This example is from Taibu, which is a shopping site where it's being used as part of the strategy in order to make sure that the shopping experience is great. And in this example, machine learning together with other acts enable them to grow by a factor of 20 in million active users. It's been used for solving scheduling and congestion, and it's also applied in credit allowances situations. And there's numerous more fields, for example, healthcare, where these technologies are being explored right now. All right, so I thought we'll take a look at a small video of what AI can do. This is an example of training an artificial intelligence to play a game. So let's take a look at it.
And the results are magnificent, amusing, weird. You'll see in a moment. These agents learn from previous experiences, and to the surprise of no one, for the first few million rounds, we start out with pandemonium. Everyone just running around aimlessly. Without proper strategy and semi-random movements, the seekers are favored and hence win the majority of the games. Nothing to see here. Then, over time, the hiders learn to lock out the seekers by blocking the doors off with these boxes and started winning consistently. I think the coolest part about this is that the map was deliberately designed by the OpenAI scientists in a way that the hiders can only succeed through collaboration. They cannot win alone, and hence they are forced to learn to work together, which they did quite well. But then something happened. Did you notice this pointy, doorstop-shaped object? Are you thinking what I'm thinking? Well, probably. And not only that, but about 10 million rounds later, the AI also discovered that it can be pushed near a wall and be used as a ramp, and tada! Got him! The seeker started winning more again. So, the ball is now back on the court of the hiders. Can you defend this? If so, how? Well, these resourceful little critters learned that since there is a little time at the start of the game when the seekers are frozen, apparently during this time they cannot see them, so why not just sneak out, steal the ramp, and lock it away from them? Absolutely incredible. Look at those happy eyes as they are carrying that ramp. And you think it all ends here? No, no, no. Not even close. It gets weirder. Much weirder. When playing a different map, a seeker has noticed that it can use a ramp to climb on the top of a box, and this happens. Do you think couch surfing is cool? Give me a break. This is box surfing. And the scientists were quite surprised by this move, as this was one of the first cases where the seeker AI seems to have broken the game. In a few isolated cases, other interesting behaviors also emerged. For instance, the hiders learned to exploit the physics system and just chuck the ramp away. After that, the seekers go, "What? What just happened?" But don't despair, and at this point, I would also recommend that you hold on to your papers, because there was also a crazy case where a seeker also learned to abuse a similar physics issue and launch itself exactly onto the top of the hiders. Man, what a paper! And the results.
So this is just a small video to illustrate what an AI can do, and it illustrates a few things where the AI, being the different blue and red agents, learn to break the rules of the game, found hidden paths which no one expected. And if you want to learn more about these types of scenarios, I highly recommend this video where an artificial intelligence agent or computer actually beat the world champion in the game of Go. And it's highly recommendable if you want to see it for many, many reasons. But my point here with showing this, and this of course is highly glamorous, is to illustrate a few of the boundaries of AIs. There are also things that an AI wouldn't do as well. And in this case, showing a recipe which was created through artificial intelligence. And I mean, highly doubt that you enjoy this recipe. So basically, we can say that any artificial intelligence does not become better than how you train it. So imagine training an artificial intelligence on a very verbal Twitter feed. You can imagine that that artificial intelligence could be quite rude, etc. So it doesn't become better than the people who train it. So that said, it's important to recognize that artificial intelligence are not aware. They're not imaginative, even though you could say that they actually create things, and they have actually moved our understanding of chess, our understanding of Go, and open up new ways to play those games. Still, you wouldn't ask an artificial intelligence to take a white a white sheet of paper and make a painting. That's not something that they are doing without training. And they're not self-learning yet. This might change, of course, and there are plenty of different discussions going on the internet on what's going to happen the moment that they can do this. So if you want to Google super intelligence, you can learn some different scenarios that might unfold. Okay, so artificial intelligence are carefully engineered to perform a specific task right now. That's important to understand, that you actually engineer and create these artificial intelligence. Now, why would you care about this at all? Well, data-driven is a trend that cuts across the industries, but what does it matter that you have lots of data unless you can put it to use? And that's an area where artificial intelligence makes a difference, because it enables you to put this data into use. Now, when I walk through this artificial intelligence, I deliberately will make some simplifications, and that's a reason to make it a little bit more intuitive. So if you're a hardcore data scientist and I don't use the exact label that you are used to, give me a little slack, because I've deliberately tried to make this presentation easily understandable and digestible, or as much as I could. So let's start with machine learning versus traditional software development and illustrate a few differences. So if you would take your average software or development process, it would be something like this. You start with defining a problem. Maybe you want to display the speed of the car for the driver. You do a model of the world. In this very simplistic example, you would model the velocity. Maybe that's acceleration over time. You will write some rules and implement that as code. And then you will create some tests to check that your complete system is working. And finally, you will deploy it and potentially will show the speed of the car to the driver. Of course, this is a happy case, doesn't always work out that well, but let's imagine the happy case for now and compare it to a artificial intelligence training. So let's shift the challenge now. Let's imagine we want to write a computer system that actually can detect numbers, the number 3. Now, writing rules that can interpret this image and tell us what type of number it is, put simply, it makes out an awful amount of rules. They're all different types of anomalies we need to take into consideration, and a number of different use cases. So what if we did this instead? What if we took the 2 middle sections, the modeling and the rules, and we asked the computer to do it for us? What we would do is we would actually create some tests. We'll say, okay, these are number 3s. And this is correct version number 3, and this is a false version, incorrect version of number 3. And we would ask the computer, say, just look at this and tell us, train yourself in making a prediction in which number is correct. And the model will tell us, well, I can detect that this is a 3. And I can also tell back that based on the training that you have provided me, I can do this with an accuracy of roughly 0.995. And that's a difference in how the process works for machine learning and artificial intelligence. We no longer tell it the rules, the algorithm finds the rules for us. So if we would jump into the workflow of creating an artificial intelligence engine, it would look something like this. The first stage is to just access and explore data. We need to gather data and take a look at it. So we will extract data from databases. You might have files. Maybe you have sensors out there from which you exploit and extract information. The next step is something called pre-processing. And here we try to clean data. We might need to fill out gaps. You might need to convert strings to categories, to numbers. We might need to do some transformation on data, normalization, for example. And finally, we might do some feature engineering where we actually make sure we have the right input, and we might do some labeling so we can explain what the data is actually meaning if we're going to do prediction. At this stage, we start with figuring out a model. So here we start the training of a model, and we do some tuning, because it's not only the model that matters. Something of the parameters to the model is also of high importance. So here starts an iterative process where we will go back and forth between a model, changing a few parameters, and check how that is performing together on the data. And finally, we reach the stage of deployment where we might choose to deploy to the cloud, but we can actually deploy the pre-trained model to an embedded device, a browser, or a multiple to different environments. All right, so let's illustrate with this as an example. Imagine that you have a bunch of smartwatches to your disposal, and you want to be able to tell whether the person that carries this smartwatch is doing a certain type of activity, like maybe he's biking. And inside the smartwatch, there are accelerometers, which can detect the acceleration in different vectors. Now, you start by extracting this data, the acceleration, into a central database. And the first thing you would do is just eyeball the data. You would explore it, check, do I have enough of it? Is it representative? Are there patterns inside it? And this is a manual task. And then you step into the pre-process stage. So you would most likely normalize the data to make sure the different features are in the same range. And the reason for this is because mostly a distance is creating in the Euclidean space. And if the ranges are completely different, then the factor calculating the difference in distance will be off. The next stage is you will do some feature engineering most likely. So let's imagine we now create a vector and we have 3 different acceleration variables, the acceleration up, forward, to the side. And we might think of that, oh, I want to actually create a feature. In this example, let's imagine we actually create a feature which is the velocity forward by taking acceleration forward times time. And in the end, we will add a label, which is, okay, this specific data point, V1, is a situation where a person was actually biking. And we can continue by labeling data. Maybe the second data point is a situation where the person wasn't biking. Now, this is where we put the majority of effort, most likely. This is where 70% of the time is being spent. And then we go on to the stage where we train a model. We need to pick one model, one algorithm, which we think is suitable for the type of challenge we want the model to predict. And we start the iterative process of testing it towards our data, tuning the parameters until we're satisfied that it can do a good enough job of prediction. And then we go to deployment. In this specific example, we choose to deploy it to the cloud on a web page where a person can see their last days of activity, a number of days the watch has detected that they've been biking and maybe doing other things. So very crude, very simple example to try to illustrate how the process could work. So that said, let's then take a step back and ask, so where would these type of techniques excel? Well, the first situation where they make a pretty good job is if you want to do real-time predictions and decisions. The second factor to take into account is that if you have many parameters and very many dependencies, this is also an area where machine learning, deep learning, and AI can do a pretty good job. And it can actually do this with a pretty decent accuracy, sometimes in the same neighborhood as humans, sometimes slightly worse. But if you combine that with other factors that it could do it with real time, that makes a case for AI. Now, of course, one constraint is that you do need to have data, sometimes plenty of it, for this to work. So there are edge cases, of course, where humans do a better job, and our human brain is quite well adapted to make predictions with very low limits, low points, low number of data points, where artificial intelligence would struggle still. So let's take a look underneath the hood, and let's take a look how machine learning would work. So there are three core elements of machine learning. First, there is the algorithm, and the algorithm can be really simple, but it's an algorithm that takes a couple of features and makes a prediction, y here. And it can actually be a fairly simple algorithm, which I will show to you shortly. And then the second component here is a cost function, which compares the prediction to real observations and just tries to calculate how far off are you from the prediction. And finally, there's the feedback function. It's called an optimization function, whose goal is actually just to minimize the error. So it seeks to make this error as small as possible. And it does that through tweaking the algorithm, the parameters inside the algorithm. And that's all to it. And the interesting aspect is that the algorithm can actually be fairly mathematical simple, but when combined with the cost function, optimization function, and several iterations, the prediction can become pretty good. So if we take artificial intelligence, we can roughly group it in three different technology frameworks. There's machine learning, there's deep learning, where the key combining element in deep learning is that it utilizes neural networks. And then there's the area of reinforcement learning, which also uses neural networks, but it's applied in other scenarios. So if we look at this, there are two different styles of approaches that you take. There's something called supervised learning, and supervised learning is when you ask for a prediction and you have already, you know what the answer should be, and you're training your agent to be able to predict what you know. So if you want to predict what type of fruit is in an image, supervised learning, you would provide the agent with a fruit and a label saying this is an apple, this is a pear. In unsupervised learning, you're actually giving the data to the agent and you are just asking it to find me the rough groupings. Maybe are there similarities, for example, in these images? And it might be so that the artificial intelligence will just say, it seems like we have a grouping called apples, one called pears, and one called bananas. But it's kind of like a categorization, basically. And if you look at the different applications that where you would apply this, there are two styles. The first is a classification. You're asking the agent to classify, is it this A? Is this a pear? Is this an apple? There's another application which is more a prediction, a continuous prediction. So think of this as a linear variable, but it's a continuous variable. And when we talk about reinforcement learning, the application is we have several different agents on a playing field that can take different actions. And we want to train a model to be one of those agents. If we would illustrate this with a few use case examples and just group them, if we take the classification example, image detection is a good example of classification. A recommendation agent can work using classification. For example, is this a frequent shopper? If this is a frequent shopper, maybe we should give them a specific set of recommendations. Spam filtering, fraud detection, is example of classification, fraud or not fraud, or detecting health, maybe detecting cancer from X-rays. If we continue with continuous prediction, something like predicting the sales price or real estate, predicting the stock price, or just the number of kilometers until the next service, that's all examples of continuous variable which you try to predict. And if we move on to reinforcement learning, here we would have the obvious example which you saw in the beginning, gameplay with different agents doing things. But also there's the example of recommendation engines. And the difference to the classification version or recommendation agents is that the recommendation would be based on real-time actions. So if the recommendation agent in classification would say, you seem to be a frequent shopper, thereby I recommend these products for you, the real-time recommendation agent will take in consideration what you've done right now. Maybe you seem to be a person that takes things in and out of your shopping basket. Thereby, you seem to be, maybe you should try these pretty safe bets. So it would make the recommendation based on real-time actions. Now, if we would just look at, so when would I apply machine learning? When would I apply deep learning? Because both can be applied on similar challenges. There is a few trade-offs here. So if you take machine learning, a good thing machine learning is that you can apply it with fairly low sample size and achieve a decent amount of accuracy on prediction. If you draw the same curve on deep learning, there is a slower, you need more data for the deep learning to be able to make a better prediction compared to machine learning. And it's a little bit slower in the development. But on the upside, if you have enough data and you train it well enough, it can often make a better prediction than using machine learning. So it's a trade-off of time, effort, data. That some can be the choice whether you choose to go through machine learning algorithm, maybe you choose deep learning. All right. So when to use which? A very rough overview. And here's where you as a data scientist excels. This is your field. This is the area where you make a difference in making these choices. I'll give you a rough guide. So machine learning, you can actually make some pretty okay predictions with limited data. Sometimes just a few hundred of data points. Of course, more is better. It's pretty quick to train. So you don't need to spend a lot of computing power in order to create some predictions. It's something you can do to explore your understanding pretty rapidly. And it's also helpful if you're in a situation where you maybe be legally or legally bound to be able to explain exactly how you came about with your prediction, then machine learning is a pretty good fit because you can sort of backtrack how that happened. Deep learning, if you compare this, you need a lot more data, sometimes in the example of millions of data points for it to make a prediction. Of course, this depends on the setup of your network. It's a bit slower to train. Here, we could be talking about anything from, okay, maybe a minute, an hour, up to a couple of days, 90 hours if we have a very complicated deep learning network on a regular CPU. Of course, I can impact this time by setting different hyperparameters and choosing, for example, to train it on a GPU. So deep learning is a black box where it's very hard to in detail explain how the deep learning network came about with prediction, which makes it a little bit cumbersome. Example, if I have this version of autonomous cars, today there are legal constraints which make this difficult. This might change, of course, but in a car, you're legally bound to be able to tell how a decision was made if it was made autonomous. And that's kind of tricky if you use a deep learning network. In reinforcement learning, yes, you need to spend even more time to actually engineer it. It's also pretty slow to train, but the good thing with it, it can be used for real-time strategy decisions. So that said, let's have a quick peek on a few different algorithms, and I'll just pick a few simple ones so you get a rough overview of what they can be. So first, very simple algorithm, and to be honest, I was quite surprised to see that this was part of machine learning, but logistic regression, which is basically the task of fitting a line through a series of data points, that's used inside machine learning. Now remember that the magic happens when you apply this together with the cost function and the optimization function. But the interesting thing is to notice that a pretty simple algorithm like a linear fit can do a pretty good job by combining it with the other elements. Now, another example of an algorithm is a version of regression called logistic regression. And logistic regression, you actually try to do a classification. Maybe you want to just be able to tell if a person is jogging or person is not jogging. And what the algorithm would do would be, based on the data, calculate the probability that you are on the other side of the fence. It would create a probability curve where if you are on the low side, here there's a low probability you seem to be jogging. Here's a 50% probability, and it's a high probability you'll be jogging. And you will combine that with a threshold to say, above this level, I will call it that this person's is being jogging. Another version of an algorithm that can be used is decision trees. And decision trees are very, very simple. It's kind of logical gates. So let's say I want to be able to tell what type of car I would choose. And I would want to be able to predict it based on who walks into the door. Will a person buy a sports car? We might create a decision tree saying, are you a male? Yes, no. No, I would predict you buy a Toyota. Yes, okay. Are you over 35 years? Yes. If I no, chances are you will get a sports car. If you're over 35 years, I will check, do you have a family? Yes, I have a family. Then you will likely get an SUV, and no, you get a sports car. So the upside of decision trees is it can be made to represent pretty complex dependencies. It's very quick to train. The downside is decision trees gets married pretty easily to your data. This is called overfitting, meaning it's easy to get in a situation where it very accurately predicts what your test data says. But if you're not careful when you train it, it will make a poorer job in the real world, generalizing above or beyond the data which it saw. So this is something you have to be careful about when you are actually training it. So these are examples of supervised learning techniques. A third one, naive Bayes, is basically a very simple probabilistic algorithm. And the most intuitive way to explain it is, let's say you have a store and you want to figure out whether to put barbecue meat in the fridge based on weather. So this is naive Bayes, and it's naive because it makes the naive assumption that the different features are independent, which of course in reality we know that they can be very dependent. But it just assumes this out of the box. So the way this works will be that it tries to predict that, given my understanding what the weather is, should we populate the fridge with barbecue? We train it and make sure it makes a prediction based on what the weather is. The interesting thing is, I know that there is an algorithm similar to this in one of our food chains in Sweden. If they use naive Bayes, I don't know. All right. Let's now look at an unsupervised learning technique. And remember that unsupervised learning was the case where we would give the data to computer and we just asked to roughly group it. Tell us what type of groups that exist within this pool of data. So in this example, imagine that we have data that tells us a combination of the number of rides at amusement parks and the age of participants. And by just plotting this data, it might look like this. We can see that there are different combinations, different clusters. And it seems like at a certain type of age, it's more likely that you will take more rides at the amusement park. So what this algorithm would do will be to try to calculate the center of these clusters. And when we have a new data point coming, it would just look at the distance to the center of the clusters, and based on that, try to make up its mind of which of the cluster it belongs most closest to. Now, by training this algorithm, we can experiment with different choices of clusters. We can plot here, you see on the right-hand side, the error we get compared to the number of clusters we choose, and we will choose a sweet spot. In this case, maybe it's 3, where we say a 3 cluster seems to be a good trade-off between the error and the prediction. Finally, we'll take a look at a deep learning network and how this works underneath the hood. The interesting aspect of deep learning networks or neural networks is that they can be applied in both the situations where we train the networks towards labeled data, so we know what the answer should be, but it's also used to categorize things in unsupervised learning. So the way it works is, imagine we are watching a drawn image in this dotted area here, and we want to train our network to be able to detect what's inside the image. So what we do is we create something called an input layer, and these are a layer of data points or functions where with the number of inputs here would represent the number of pixels in the image. So if we have a 64 by 64 image, we might have 64 times 64 inputs. Then we choose an output layer. An output layer, we choose nodes which represent the data we want to predict. So in this case, let's imagine we want the network to predict if it's a square or it's a triangle, if it's a circle. This is a categorization challenge. Then we might choose 3 output nodes, and if we get a 1, we would say this is most likely a square. Now becomes the decision point of hidden layers, and these are the layers in between. And this is something that we would engineer and tell the network maybe should use 1, several, and how they should look. And in between each layer, we will have relations or dependencies like this. And what will happen is that the information will travel through this network through a series of functions, and when it comes to the output node, we will get the decision whether this is a square, a triangle, or a circle. So let's take a quick look at the math. So imagine we step out in a very, very crude, simple neural network, which just has an input layer and an output layer. So no hidden layers here. Now, the way this works is, imagine the x1 is a simple number, 1 to 10, which gets forwarded in the network. Then there is a linear function called propagation, which actually takes this input and propagates this over to the output node. And this is combined with a weight, the W, and something called a bias or a constant, B. And what we'll do to calculate the value that comes to the output node, here GZ, is we'll just sum up the combined value that's across all the different nodes. So we'll just make the sum of all the linear functions, And then we have something called the activation function. So we'll take this value, and the activation function will decide whether this value gets transformed or forward to the rest of the network. There are a couple of different choices here. This most simple, crude choice will be a step function, where we say if the value is less than the threshold, we should forward 0. If it's higher than the threshold, should forward 1. It could be something like a soft step sigmoidal, where it would take a S-curve shape. Or it can be something like a softmax function, which is something is used in categorization problems, where the most intuitive way to explain it is that it will try to calculate the probability that it belongs to a certain category. There are, of course, a lot more functions or algorithms here. And this is part of our tuning when we set up the network. We need to make some choices. Depending on the problem, what's the number of nodes we're going to use, what the setup of the network is going to be, what type of activation function, etc. So what I hope to show you is that the algorithm itself inside here actually can be fairly simple, and the math inside can actually also be fairly simple. But when combined with the learnings, they can actually do a pretty good job at prediction and classification. That said, let's take a step back now and just think of what does this mean for architecture. So the first point here, when we talk about architecture, is that if you're in a lab environment and you just want to do some labbing, architecture, don't need to think so much about it. But when you try to scale this, then architecture starts to make a difference. And I'll highlight a few areas where you need to think a little bit. And the reason is because if you don't think about this, you'll get bottlenecks in your workflows. Training might take long, moving into production might take long, and you don't want bottlenecks. So let's highlight a few areas of consideration here. Okay, so first area, which we do need to mention a little bit about, is security. Because, well, you are going to expose maybe a lot of data. And it goes without saying, if you study the media, that this comes with some concerns. So you need to think a little bit about where to keep your data, and maybe also about how to anonymize it to make sure you keep integrity protected, because you can make pretty good predictions with large amounts of data. So you need to take this into consideration. Where to keep your data is also not only a security concern, because when we talk about scaling, if you're going to join data, group data, keeping it a central place, or where that central place is going to be hugely helpful to be able to speed up the process when you start to do data operations later on, grouping, combining, etc. The next area of concern is reproducibility. So remember, in the process, we are doing some ad hoc operations of the data. We're doing transformations, we are doing feature engineering, and you're going back and forth iteratively, saving, changing data. And you want this result to be able to be reproduced to your test environments and to your production environments. So thinking of tech frameworks and architecture that basically can take this data manipulation operations and reproduce them at scale in many different environments, it's something you want to pay a little bit of attention to. With a good stroke of luck, maybe you have support already here, but this is an area where you want to think a little bit about. Portability is basically the ability to train once and deploy to many. Maybe you want to train it on a GPU, maybe you want to train it on a CPU, but once you train the model, you want it to be able to very easily to be deployed to a cloud, or maybe you want to deploy it inside a device or in the browser. But the tech frameworks which you choose should support this train once, deploy to many. And final point here when it comes to scaling is the agility aspect, whereas, okay, imagine you're taking this out to production, you do want to make sure that you employ versioning, like a versioning control system, because you're going to do frequent iterations and update. Also, it's very useful if you have ways to detect that once you put your model out in production, if it's drifting away, and you can detect if this is happening. So you want to check that that is happening. And finally, retraining. So once you put your model out, then it's a time for, you want to be able to retrain the model and make it updatable once it's out. So I'll see a couple of raised hands, and there will be an opportunity by the end for some Q&A. So at this point, please, save your question, and we'll make sure you'll get the time to ask it when you come to that part. Right. Of course, if there is a very specific comment, you can post it in the chat. I'll do my best to see if I can catch it. All right. So when you think about the architecture here, it's important that you think of two aspects. One is the scaling, and the other aspect that you do want to take into consideration is that you want to be able to make sure you can follow the flow end to end. Because what good does it do if you can employ this in a lab? You do want these predictions to be able to be put to use in a production environment or put to a client. So I will illustrate two tech stack examples where you can take this full journey end to end. Of course, these are not the only examples out there, but there are two pretty good examples that do this. So first tech stack example is MATLAB. So MATLAB is an integrated environment which, if you've done simulations, maybe at university, you might already stumble upon it. MATLAB does a very good job in making the process smooth, the iterative process between going back and forth between accessing your data, developing a model, and it also enables you to deploy the model to a MATLAB production server if you want it in the cloud. But the interesting aspect of the MATLAB is that you can actually generate code based on your model, real code, which you can put in any environment because you can do the plumbing around this code yourself. Now, the other ecosystem, which is a very popular one, of course, the Python ecosystem. So here, a couple of examples. Keras is, I'll start from the bottom. Scikit-learn is the machine learning toolbox, basically, inside Python. TensorFlow is the neural network or deep learning toolbox. And Keras is basically a high-level API on top of TensorFlow. So it just tries to make TensorFlow operations a little bit more user-friendly. Now you can employ this tech stack examples using, for example, Google Cloud Machine Learning Engine, and through that get a REST API, which you can use. So actually an API you can use in the cloud. Of course, there are more tech stacks examples, but I just wanted to highlight a few which are worth exploring because there's huge use. There are quite a big user base. There's quite a lot of material out there. That said, this is a field that is evolving quite rapidly right now. So this field will look different in 2-4 years, way different than now. And this is kind of a battle going on right now in being the front runners inside this framework. So expect change in this area. So now a question. So all this, is this a game changer? Will this change things, and so for whom? Now, I will take myself the liberty of doing a little bit of speculation here. And the reason for doing this is because I believe that if you can visualize the future, you can impact it. But if you can't visualize it, you will get hit by it in one way or another. That said, of course, I mean, you can take this with a grain of salt, so take a step back and make some own thinking about this. But that said, you know, let's have a look at how this can impact a number of different roles. So the first thing I'm going to point out is, if you look historically how automation has been applied, we can categorize different steps. So in the beginning, you would have a repetitive manual tasks being done by robots or machines. We start to use computers pretty early to do calculations for us. And then we evolved, and I think the stage we are quite now is that we try to digitalize our workflows, and we try to make the computers help us do that. Now, the interesting aspect is that until now, computers and robots have done this better. They are quicker, they're more accurate, they can do this 24/7, they don't need sleep, etc. This part so far has been reserved for humans. If you would step into your ordinary or everyday company, making the decisions, the calls, has been something that we and humans, yes, we are, you know, our brains are pretty good strat for it, but it's been the job of us. Now AI shifts this balance. So if before this was pre-AI, you can say that very soon we'll be here, where not only will they be quicker in making the decisions and predictions, they will actually do a better job at it. So the amount of work that is left for the humans will shift. Of course, this will take some time, and this is maybe the most uncertain variable, how quickly this will happen. So this is a game changer. I'm going to illustrate this for three different roles here. Let's first take the development example. And if you look at the process we had before, you can basically say that this is a game changer for a developer, because who needs me to write all that code, right? All those business rules is something we let the machine learning agent to actually figure out. Now, of course, we're going to need developers because the infrastructure, the plumbing that goes around it, and of course, there will be use cases where we won't use AI, but the role will change. And the skill set required to deal with these challenges is different. So you could say developers are very well set up, being quick learners. I mean, you know the computers, you know the plumbing, the continuous deployment systems, moving data. However, it's also important to recognize that you need things like statistic knowledge and knowledge of how the different algorithm works in order to do a good job in machine learning. So let's take another example here and look at the business owner. I will illustrate this again using an example. What could it mean? So I've chosen an example here of a public sector department in Sweden, the Swedish Social Insurance Agency. Now, I chose this because the services that they provide are, you know, intuitive understanding, intuitively understood to most Swedes, and because you can actually look at the services you can on their web. You can they're transparent with what services they provide. Now, that said, I could have picked any other example. I could have picked a bank, for example. So don't get hung up with this specific example. I just wanted to get you a rough understanding of what it could mean. So the way the process works, if you want to get an allowance or some money, is, of course, if you're a parent and you want to get some childcare money, you apply for it. They process your application, they check that you have the right input, they make a decision, and they send out the money. If you're okay with it, then you get the money back. So I did a very simple categorization of the different services from Swedish Social Security Insurance Agency, or as we know, Försäkringskassan. And this is rough and crude, but it illustrates something here. If you just, when I took the services and I made a categorization, which could be completely automated, like end-to-end automated, which are we a little bit uncertain about, and which are completely unknown. In this simple analysis, roughly 81% of the services provided should be able to completely automate them. And just play with the thought, okay, if this is true, what would that mean? So if we compare it to the current situation here, the time to get help, or for example, the lead time to get sickness compensation for a citizen in Sweden is, as of 2018, it was roughly 120 days. So 120 days from where you did your application until you got the money, or the decision that you wouldn't get the money. Now, of course, 120 days is quite a long time, 4 months. So you probably would do quite frequent calls, checks with them to check where is my application? Is it stuck in the process? Now, as of currently, they employ 14,000 employees. And now let's imagine now that, let's play with the thought. We've done the automation, so we're taking all those 81% of the services, we were able to successfully automate them end to end. What type of opportunities would that create? Well, if this automated end to end, I did a very crude prediction that means that the time to get the sickness compensation, that should be able to shrink to a range of between 2 and 7 days, with the happy case maybe within 1 day, because if you automate the process, you make the payment, it should be more or less real time. Of course, things aren't always the happy case. You'll need to complement with some information that comes from other parties, etc. But you can make your own prediction of how much time could be reduced. In any way you cut it, you can see that you can achieve a pretty radical drop from the original or the current situation of the lead time. Now, of course, you can make the same type of guess on how many employees would they need once you've done it. Of course, the skill sets will be different. I'll let you think for yourself of how close to 14,000 will be, or how off with 14,000 will be. But of course, this provides an opportunity that you can shift the employees to other parts in society where they can do preventive efforts. So is that a game changer? Well, of course, this comes with a cost. I mean, this won't happen monetarily. You need to invest yourself to get there. But yes, you can get your business to run faster with lower cost of operations, no doubt. And if I take my own field, where I work quite frequently right now as an agile coach, it's pretty interesting, because if you're asked to come into a company and do an agile transformation, maybe our job should be to say, well, instead of transforming the existing processes, maybe we should do just some machine learning to change those processes before we apply agile. That said, applying agile is of course good in a way, because it makes the risk of making a change to machine learning easier, or any change program that you run, of course, will run smoother with less risk. So doing agile is of course a good approach, regardless of what type of change you see before you. All right, so that's it for my presentation. We will move to Q&A. My call to action is just to say that if you have a business challenge that you think could be solved using machine learning, then we are setting up something we called CRISP AI Labs. And if you'd like to collaborate with us to solve your business challenge, I'm just going to say, let's talk. Give us a note, and we'll see what we can do.